All right, so I'm going to start a new series and go in the description to see what I'm talking about and if you're actually interested in. But basically, I'm going to speed run the explanation of every single problem on a module. Just read the description, and you'll see what I'm talking about. So once you've read the description, then you can come back. But essentially, I'm going to do this as fast as I can. And yeah, let's put the stopwatch and ready, set, go. All right, so let's do static range sum. So you're given a non-negative integer sequence a1, blah 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 blah. You want to find the sum of a segment. Well, what I would do is I would first pre-compute the prefix sums. So let dp of I equal a1 all the way to a2 all the way to ai, and if you have this, then all we need to do is, assuming that this is one indexed, always one indexed your prefix sums, we just need to print dp of B, or technically in this problem it's used, I'm pretty sure it's dp of R minus dp of L minus 1, and that's our answer. Okay, cool. So that's the logic for this problem. All right. Um, okay, let's move on to subsequences summing up to 7. Farmer John's, they would like a tendency, blah, blah, blah. I remember this problem. So essentially, what you want to do is you have these cows, right? Um, and you have an array, or not. Oh wait, we had to do breed counting first. Sorry. So breed counting is this. They're numbered 1 to n. Okay, so basically, for breed counting, you have like an arbitrary array. I think it was 2 1 1 3 2 1. Okay, 2 2 2 1 1 3 2 1. Right. So basically, we'll have three arrays. I'm gonna assume everything's one index for like simplicity for explaining. Right. We'll just keep this in a multi-dimensional array. So this will just be have three arrays, right? Sure, I'll do this. You'll see why. And then we have like whatever the n is. Okay. So then essentially, we'll do uh prefix of one I is equal to uh so if ai in general, I'll do prefix of let's do this, right? Let's say prefix of ij is equal to if a sub I is equal to I, then it's basically prefix of I j minus 1 plus 1. Also, it's just prefix of I j minus 1. So, and then I is in the set of 1 2 3 for each breed. All right, so that's basically the solution for this problem. So you probably didn't understand what I did, but that's the solution. Remember? Okay. All right, let's do hoof, paper, scissors. Or no, let's do subsequences. Um, yeah. Okay, so Farmer Johns are sitting in a row. They have a tendency, blah blah blah. So um, basically, you have like an array. So 3 5 3 5 1 6 2 14 10, and you notice that what you need to do is you need to find the longest contiguous segment. Essentially, you need to find the longest contiguous segment that has a that's a multiple of 7, that all the elements add up to a multiple of 7. So what I do is I have this dp like for pre-computation. Let this equal dp of I minus 1 plus a sub I, such that a is the array, but except we just do mod 7. Okay, and we want to print out the biggest segment. So what I would do here is, okay, so there's six possible values in modulo 7. So what I would literally do is just have like a map, um have a map, right? um 1 0, this, or actually, so I have a map 0 1 2 all the way. Actually, this, hold up, just have this. So this is the keys, right? 3 comma, yeah, all the way to 6, right? Have a map, and then each time you have like a residue of 0, you put, um each time you have a residue of 0, correct, you put the index, the prefix sum that gave you that residue, or so for example, if the prefix sum of I is equal to 0, you have like an array list, right? So you have a map for the residue, and then you have an array list. So this is like, or an array, like, yeah, make this an array list. You have I1, I2, or whatever, all the way to IN, right? And then the idea is that you'll have, like, so in general you'll have a residue, and then you'll have a list of all the prefix sums that have that residue, right? Also, and then what you'll do is that you notice that you're going to linearly add this, right? So you'll just take, so what you would do for each one of the keys of this, you would just take the last element in the list minus the first element, and that would be the max answer, such that um and that would be the max answer for that. And then you would do that for each residue, and this would work in linear time. You could do this in linear time, and that should be your answer after you have the map. It's just going through 6 keys. So yeah, that's the solution here. And you notice that it always be the last minus first, because you're going to add them linearly. So you're gonna always add the first index first, like last in. So it will be sorted. Okay, so that's how you do that problem. You probably, there's probably a better implementation, but I don't care. Like, just do that. Hoof, paper, scissors. Oh shoot, I need to read this again. Okay, size. Yeah, hold up, I need to start reading it. Hmm. She tends to play the same gesture mode just once over the entire set of games. Hmm. Hoof, wait, hold up. So H is greater than S. S is greater than P. S is greater than P, and P is greater than H. Okay. This is obviously not transitive, as you can see, but whatever. This is just the rules of the game. And for example, she might play Hoof for the first X games. Okay. Given the sequence, print the number of. She can only change gestures at most once. Okay, so this should be pretty easy. Uh, in general, so you want the maximum numbers. So obviously you're gonna have to pre-compute how many P's and how many H's and how many S's are in a prefix, right? So we'll have like a 2D array, whatever, and this will just be, I let this equal like basically let this we'll just have an array of 1D prefix sums, um and each array will be like how many, basically apply breed counting to, like I already explained breed counting, right? So I think this is fair, right? Apply breed counting to this problem to basically calculate the amount of p's or h's and like s's there are at a particular point of the array or prefix of the array. And then you know that for the first x games, or basically for the for the first like for the xth prefix, right? For the xth prefix, she plays one move, right? For the xth prefix, and we're trying to figure out what's the optimal xth prefix. And is so um I think you can loop. So what you can do is you could just try each one. So try each. So there's it's the x prefix. So try. So x can basically be from 1 to n, right? But then we note that if x is from 1 to n, we know that we can try x from 1 to n, um right? And we could do three different cases, because there's only three gestures. We first do the case where she does h, and then we then do the case for each x, right? For each x, and then we do this for h, we do this for s, and we do this for p. So like let's say for the h case, right? For what we do is we look at each prefix from 1 to n, and then we note that we also need like a suffix too, because there for the remaining n minus x games, or you don't really need a suffix. You could just use like you could just do like a prefix query to get the amount of x n minus x games. But then we know that the answer for this one is just gonna be like prefix x this would prefix x, right? Or dpx, whatever, right, such that dpx counts like the amount of like h's or whatever, plus you notice that it'll be, since it's from dp n minus dp x minus 1. But this is but you could do this for, so there's, after she uses dp of x, like she does like a certain gesture for this one, then there's two gestures for this one. You just take the maximum of both of those gestures to add up to dp of x. And then you can, so first you could loop through this, would just be 1 to n, and then you loop that for h, and then you also loop for s as well, and then you also loop for p as well. You do like three separate loops, and that should be the solution to the problem. I'm pretty sure that's right. It's just, yeah, you just loop through each one. Okay, so just to make sure. But yeah, that's what you would do. You just check. You just do three different cases, and yeah, and this is just OVN. So that works. Technically, it's OVN and 9n, but yeah, just showing you that that's the solution in case, because I kind of explained that terribly. So, but I'm not supposed to explain as fast as I can. All right. Okay, given an array of n integers, your task is to count the number of subarrays having some x. Okay, so having some x. Well, what you would do is um basically this is where you use a map. I don't think you can. Yeah, this is where you would use a map. So if you have like DP, what you're going to do is you're, let's say DP corresponds to this sex. So P1, P2, P3, right? All the way to like PI or PN, or all the way to PN, right? Let's say DP is in that set. So for PI, for that prefix sum, you note that you need you're going to treat, so basically treat PI as PI is um the endpoint of your subarray segment. Treat pi as that's your endpoint, and then the start point that you need is, because you need pi minus start point, is equal to x. So the start point that you need, which is s, it needs to be pi minus x. So you know that you need pi minus x. So then what you can do is that you can loop through each one of these prefix sums and then just have like a map. So map that puts uh like the frequency of a prefix sum. So like you like have some prefix sum, and then we have the frequency of that prefix sum. So the frequency of p sub I. So like basically like you'll have a map that counts how many times that prefix sum has occurred as you loop through the array, not in total, but like as you loop through the array. But like as you loop, you have a map at that point that tells you how many times like a prefix sum has occurred from p0 to pi minus 1, and then you check how many times pi minus x has occurred because that's what you need, and then the frequency of that would just be the sum, because that would be the amount of subarray segments that add up to x. So that's what you do, and that's basically the solution. Now we need subarray divisibility. Given an array, your task is to count where some is divisible by n. This is the same thing. This is just prefix modulo, right? So you let dp of I equal the other one. Let this equal dp of I minus 1 um, plus a sub I, and then you just mod n, right? And then you know that let dp equal, like, instead of prefix sums, we'll do like residue sums, because that's what it is. So R1, R2, all the way to Rn. And then you know that for Ri, you need since you need Ri, you actually need Ri, because you know that Ri minus the residue has to be 0 because it's divisible by n. So and you know that the residue will just that represents the residue, and you need that represents the residue, so you need it to be 0 essentially. So um well so since you need that to be 0, then basically for an Ri you need an Ri or some Ri minus k, such that like k is positive, that equals Ri. This is what you need, because you need the same residue, right? You have this prefix sum that computes like from 0 to I, the residue. When you calculate the sum of that, then basically you need to subtract then you need the residue for a segment a to b. You can get the residue from 0 to b, right? And then subtract all the residues from that in mod 7, and then that's your answer. um that's the answer for that query. So then you know that when you do the differences of proof sums, that's going to give you the residue for that segment. So then you need the same residue. So what you do is you just literally have a map that counts the amount of times r sub I has repeated before you've seen, like, before you get to r sub I, how many times has r sub I repeated from 0 to r sub I minus 1, and then that'll be your answer basically. All right, let's move on to, because we finished this one, so we're almost okay. Why did the cow cross the road? Okay, the long road through the farmer John has n crossroads, a convenient number to n, to allow cows to cross at these. Just it's okay. Wait, hold on. Wait, hold on. I actually haven't this problem in a while, so I need to read this. Wait. So okay. So essentially, you have like an array, like you have one, two, three, all lined up, and um, some of these numbers or cows, whatever you want to call them for simplicity, we'll call them numbers. Some of these numbers have are broken, but you want the minimum signals that need to be repaired so that there exists a contiguous block of at least k working signals. So essentially, for a segment, you want k working signal, or let's say a segment contains let's say a segment from a to b contains, so we want, let's say it contains x working signals, right? Then in order to repair x working signals, we take b minus a plus 1. It already has x working, so that's the answer. It has x working. We basically want to minimize this across all possible segments. So what we can do is we need to know like how many broken signals there are in a segment. And what we can do is we can do like prefix sums for that. We can do prefix sums for that. And then we note that if you have prefix sums to compute like dp of I, compute how many or number of broken from 0 to I, let that be pre-computed. Then you note that this is basically what we're trying to minimize. We obviously can't go through the n squared segments because that's going to be too slow. So what we need to do is we have to loop through each one of when we pre-compute it, we need to loop like for a dp of I, we simulate this as it's the start point, and we simulate like dp of I as it's the end point. And actually, these some contiguous block, I have at least k working signals. I think for this segment, do you only have to look at I minus k? Wait, is it like does the block have to be length of k? Is that what I'm? Wait, hold up. Does the block have to be length of k? Hold up, let me read this. I'm kind of confused on the wording of the problem. Hold on. Given a list of of at least k working signals. Um. Well then, don't you just need to? Oh, in order for there to exist some contiguous block. Oh, so it has to be contiguous. Oh, okay. So this has to be contiguous. Okay. Okay, so then that makes sense. Okay, so then for dp of I minus 1, right? For some element like, so dp of I minus 1, if you get to the a sub I element in this 1 to n, right? Or whatever, you note that first of all, it has to be a block of k contiguous elements, right? It has to be a block. So you know that like you could simulate this as this is the endpoint of the segment, the subsegment. You're only gonna look at this, some a sub I minus k. If this is plus 1, whatever. If that's probably plus 1, right? To be like who, but who cares about the plus 1 minus 1s for now? But you're only gonna look at that segment, and basically when you look at that segment, you're going to just you already have prefix sums, right? So basically, for each one of this, what you're going to do is you'll just minimize so you'll basically minimize. Let's say it has X working signals, right? Uh, you just minimize um X minus or or technically it's gonna be, so we know that it's gonna be length of K, right? So it'll, let's say there's X working signals, so it wouldn't just be X minus K, because oh no, it would be K minus X. K minus X, my bad. So basically B minus A plus one will always be K. I kind of misread that problem. B minus A plus one will always be K because you need K contiguous anyway. So if you simulate like an element that like it's the endpoint, like of the segment, you need K of them anyway. So like so obviously what you need to do is just look at that segment from this to this, and then just minimize K minus X, and you can just pre-compute that with prefix sums. So yeah, that's the solution for this. Haybale stacking. This should be. I actually remembered this problem because it's a very fundamental problem. So let me just read this though. The median head of a. Wait, what? Hold up. Let's know the. Oh, I didn't know they. I forgot they had a median. Okay, wait, let me just read this. Okay, so we basically want to know the median number of like cables or. Okay, so basically we have like a bunch of elements, like a bunch of slots, right? We can have like, so the slot one, slot two, slot three, all the way to slot n, and basically each time we have like we're given a query, segment A to B. We obviously know that we can't brute force this question because it's gonna be too slow. So instead of brute forcing this segment, we know that let's say A is somewhere here. Then we know that all we can do is we can put a one on A, and then when we put a one on A, we can put we can put we want we can put, yeah, we can put a negative one on B plus one, because we want everything from A to B, so A to B inclusive. I should probably yeah, we want all this to receive a one, so then we can just run a prefix sum, and then once we run a prefix sum, we can get the amount, and then it's just trivial by then. This is known as a difference array. So yeah, this problem is pretty trivial, pretty if you know difference arrays and prefix sums. So yeah, that's the solution for this problem. Good Subarrays. I also remember this problem because I actually like this problem. It's actually pretty. It was pretty difficult. Well, it was not difficult. It was clever. It was difficult to see at first, but you have to do some mathematical manipulation basically. So you're given an array an array of 8 to 1. Basically, you let a subarray be called good if the sum of the elements of the subarray is equal to the length of the subarray. So essentially, um, what this is saying is that if you have, let's say you have some segment A to B, right? Let me use the inclusive. So I should have. What, well, we know that the length of this is, and we want to count the amount of good subarrays in the array, right? What is this? Okay, so you know the length of this is going to be B minus A plus 1. So basically, we are looking for dp of B minus dp of A minus 1 to equal b minus a plus 1. Okay, here is the very clever manipulation that I honestly am not gonna lie, when I did this problem, I did not think of, but at least I remembered it. I didn't prepare this beforehand, by the way. But here's the clever manipulation. What you do is you do dp of b minus b, and then you manipulate it like this, and you'll see why. It's just it's kind of like a contrived manipulation, kind of. It's just like, how would you think of it? And then minus, this is technically minus a minus 1, right? And then you know that let a minus 1 equal u. Just let this equal u. Then we have dp of b, and we're just manipulating it. We're like, this is just how the problem's defining stuff. This is basically the problem statement. We're just manipulating it. You have to manipulate it. They never give it to you in the form that you like it. So this is a good lesson to change the forms of things, right? So minus u. Well, hey, look, we're basically looking for all pairs u and b such that this is true. Like, uh, if so, basically what we can do, um, we can just have a map that puts, like, for a dpi minus I. We can have a frequency. So frequency of dpi minus I, right? We can count how many times does, because basically we need to pick um all pairs u be such that that's true. And what we can do is we can just have a frequency map of this, right? And then you can just do like the length of the frequency map. It would just be like the length, like, so n choose 2, or like, let's say it has like n, so then you could just do n choose 2. Like, let's say the frequency of this is n, then you could choose 2 of those dps, and then that's the answer to your problem. So the idea is that you just manipulated it. And yeah, i I honestly, this is very clever. So that's always time, but yeah, I kind of really like that problem. It's really nice. It's just manipulate, like some algebra. So GCD on a blackboard. Oh my god, these problems are getting tougher, as you can see. Oh, this was not that bad. This one was not that bad. Yeah, this was pretty easy, actually. So there are n integers, a to 1, a1 to an. Written on a blackboard, you will choose one of them and replace it with an integer of your choice. Find the maximum greatest common divisor of n integers after your move. Okay. So the way this problem worked is that, like, let's say you have a sub 1, a2, a3. Let's say a sub I is here, and then a sub I plus 1 is here, a sub I plus 2, and then all the way to a sub n. We note that like, basically, if I decide, so we want the find the maximum greatest common divisor after you remove like one thing. So, and replace it with an integer of your choice from 1 to 10 to the 9. This thing is actually useless. This is useless, honestly. This is literally so like, I think this is what distracted me. But let's not talk about that. You Yeah, don't actually simulate the replacement. And my time is going. So basically, what you do here is that if you remove a sub I, right? Let's say I remove this element, then basically the answer to this, let's say the replaced element is R. Let's say I switch a sub I with R, right? Then notice that it's the GCD of the GCD of um a sub 1 to a sub I minus 1. Um we know that it's the GCD of this, comma, the GCD. Wait. I think it's also the GCD of um isn't it I plus 1 all the way to a sub n? The GCD of this. So the GCD of this prefix and the GCD of this suffix, comma. You note that Okay, well, if it's the GCD, obviously you're going to replace it with the minimum of, let's say this was, or the minimum, or wait, I don't even think what you replace it matters though. Does it even? It doesn't matter though, because this, well, it has to be. It can't be bigger. In fact, if it's bigger, then there's a problem. So you're gonna just, like, let's say this is A and B, right? So let the GCD of, let this be equal to A, right? So the GCD of this segment, of the blue segment and the red segment, let that be equal to A. So if you find the GCD of the blue segment, then find the GCD of the red segment, and find the GCD of those together. That would just be A. Um, yeah, that's kind of. There's not really any other way you would do this. So you'd have to do prefix GCD and suffix GCD, obviously, and then you can easily find it. And then you note that if this is A, well, then the answer would just be GCD of A, and then obviously, like like what you replace it with, you can't get a bigger GCD, because you know that, like, if, like, let's say the replace element is bigger. Let's say it's A plus K. Well, you notice that the biggest one you can now achieve is already A. And so then if you make it smaller, so the answer is just going to be the GCD, the max GCD prefix and the max GCD suffix. Like, so what you replace it with really doesn't matter, because you can't really do better. You can always replace it with the GCD of A. You can always replace it with this A. So what you replace with doesn't matter. That just kind of throws, that was just kind of there to throw you off. And let me make sure I'm correct on that, because these problems are getting obviously harder, right? Yeah. See, it's just the maximum of this. You don't actually care about what you replace it with. I remember that. It's just to throw you off. And okay, so let's move on to multiple of 2019. This problem was annoying. This is a hard problem, bro. What is this? 30, 40 minutes? Oh, bro, look at this, bro. We're gonna have speed run. All right, let's speed run this one. Speed run the harder one. Okay. Okay. Given is a string of s consisting of digits 1 to n through n. Find the number of pairs of integers that satisfy the following condition. That's multiple 2019. So they give you a carry rate, or you want to. Oh, okay, multiple of 2019. Oh, this one. Oh, that one's difficult. This one's difficult for sure. This one's difficult for sure. You can't speed run through this. But this was like a very mathy, from what I can tell. So you have like a string s. They give you like arbitrary numbers. I'm just gonna just so like, yeah. I'm not really gonna do no. Or let's generalize this. Let's say s is the string of digit 1, digit 2, digit 3, all the way to digit n. So let's make this more general. Let's say if d4 all the way to like uh d sub I, like, because I'm gonna make some generalization of d sub I to generalize this. D sub I plus 1. This is, oh wait, this is digit. Actually, this should not be commas. This is a digit, unless it's like 100,000. But like, let's not do that. D sub. All right, so this is d1 all the way to dn. Okay, so essentially what you need to do is for a d sub I, for d sub I, you want, you let's hold up. Notice that s is also equal to like technically, actually, I should have done this. I should have actually numbered it from. Mm, yeah, I should have done this and said, like I messed this up. D sub and D sub. Let me rewrite this as okay. Actually, do this D sub and um, because um, this is a waste of time, but this problem's already difficult enough. So, well, it's not that bad, but like it's just annoying. Right? Let's say this is like D sub zero. I don't know. Okay, or D sub one. We always one next. I'm a one nixing boy for life. Okay, so like, notice that this is also equal to like if you write this as the sum of power, like you can write any number as a sum of powers of integral, as a sum of integral powers of 10. Like you basically like for 653, you can write this as like 6 times 10 squared plus 6 times uh 5 times 10 plus 3 times 10 0, right? This is just basic base number arithmetic, right? So for basically like for d sub I hold on. All right, so then notice that um okay, but yeah, this is just I had to pause it for a quick. This is just base number arithmetic. So how do we proceed? So for D sub I, we're gonna like I said, for like the theme for like problems like when you have like queries of like a comma b or I comma j, the theme is like you fix like an element as the endpoint or the start point of the segment. In this case, I'm going to fix it as the endpoint. So if I fix this as the endpoint, then I need or technically j is the endpoint. Okay, let's say this was j then. This is gonna be badly explained, but yeah, why is this? This should be j minus one and j minus two. Okay, you probably didn't care. He probably knows that. But if I fix this d sub j, right, then I need a d sub I. Like I need a d sub I such that the residues it has to be a multiple of 2019, right? Wait, so what I can do is I can do that's not that bad. What you can do is you could just do prefix mod. So let dp dp at I represent d1 times 10 to the power of 1 plus d2 times 10 to the power squared all the way to di times 10 to the power of I, all this nonsense mod 2019. But technically you can replace this actually. So what am I doing? So you just saw what I did. So technically I could just replace this dpi minus 1 and then plus di times 10 to the I, and then you could just have like a running loop or something. And then if this is true, then for d sub j, right? So for dpj, then you need you need a dpj to equal some dpi, right? You need like a map that counts it. You need a and then so they can have the same residue. Or actually, instead of doing that, I think what they did in the solution, if I remember correctly, is that they just you can just do like you could just choose two. So put the amount of times like that appears, right? Like calculate. Oh yeah, instead of doing that, you could do a map, but an easier way is just to like do a frequency map and then just do like choose two. But yeah, that's actually not that bad. Why is this even rated hard? No, before it was really hard for me, I think, or yeah, but now it's like really easy, I guess. Just doing hard problems. Yeah, this is okay. So that was pretty easy. Actually, it's not even that bad. Wait, do they have a video of this? What? Dude, it's not even that bad. Wait, they had a video of. Okay, we're wasting our time, but like, what the? I'm not even gonna say anything because I struggled on that problem. I remember, and then they're freaking okay, whatever. Not even gonna say anything about it. But yeah, we got the solution. It was not that bad. And make sure I've obviously already seen these problems before. Like, there's no way I can be solving these problems so easily. But it's a good review before I go on to the next module. Um, let's move on to. Bro, do I have to do these force queries? You know what? I'm going to trivialize this. Force queries. What do we want? We want the amount of. All right, so basically, just have like a matrix, a 2D matrix. Um, so it's like 0, 1. So just, yeah, just have like a 2D matrix, whatever, and then just compute 2D prefix sums. I would zero index, and then 2D prefix sums would just be this. This is the formula, right? DP I'm -1. I'm not gonna derive it here. I don't have time, but then you just do J DP I J -1. I actually what I do here is I do this, or yeah, I can do this. This is how I actually write my instead of yeah, I initialize dpij as the actual element. So yeah, and then basically we can do that, and then we need a query. So we for the query, what's the formula? I would just search it up. Let's just say I think I forgot the formula. Well, I know this formula. This formula is I didn't really memorize it. You can easily derive this one, but like the one for a query, it's like the formula's down here. I don't really think that's worth committing to memory. Like I can get the formula. And yeah, you can derive it, but yeah, I would just use this formula and then boom. It's just a straight application, whatever. Oh wait, okay, what max Subarray Sum? Oh wait, I did force queries before I did max Subarray Sums, whatever. Okay, screw it. Okay, so let's do max Subarray Sum, I guess. Max subarray sum, you already know what it is. You want contiguous subarray. There's actually two ways you can do this. One thing you can do is you can keep a running sum. So have a running sum and then keep track of the least element that precedes it, right? So like for an element a sub I, have a running sum from elements like I a sub 1 to a sub I, have a running sum, right? And then keep track of the minimum. So this is this minus the minimum of a sub 1 all the way to a sub I -1. Right? Just keep a running sum and a running min. Boom, trivial. Um, because you can define the sum as just the difference of like prefix sums, um, or first or not the minimum element, the minimum prefix sum. So this is actually wrong. This is the minimum. First, you actually have to, yeah, never mind. You have to pre-compute the prefix sums. Yeah, just pre-compute. So pre-compute the prefix sums. You can't do a running sum. Pre-compute the prefix sums, right? And then for a prefix sum, you need minimum. So p sum or dpi minus minimum of dpk such that k is from 0 to I-1. So that's basically you want the max of all that across everything. You're basically optimizing um the n cases, whatever, like each case, and yeah, and boom, that's how you do it. The other way is you can use Condain's algorithm. Condain's algorithm is like you loop through, right, and as soon as the sum goes below 0, right, you start a new sum, and then boom, that's good in. So we solve that, and we solve first force queries, paying the bar and silver. Um, basically paying the barn. I remember this one. Um, So we want to see how many times, like how much area is covered. Well, we can. I'm not gonna read this because I don't I only reread if I need to remember. So basically, what we can do is we can turn this into a 1D problem. If this was a 1D problem, we would see how much the length is covered, right? And if you have A to B and we want to cover we know that we want to cover like distance, then the distance from A to B, so distance of A to B is the same as the amount of numbers from A to B minus one. So what we would do is we make a difference array like this, put a one here and put a negative one here. In Haybale Stacking, you did it on B plus one because you wanted to know the amount of numbers from A to B. But this case, you want to know the amount of numbers, the amount of the distance from A to B, which would just be a little bit different because it would be the amount of numbers from A to B minus one. Um, Obviously, you can verify that yourself, and then we need to apply this to two dimensions, right? If we apply this to two dimensions, we have this dimension here, we have this dimension here, and then we know that, okay, we already solved the problem for this line, so we know that if there's a 1 here for this line, we're going to need a negative 1 here. And there's a negative 1 here, we're going to need a 1 here. Opposite, it would just be the same logic. And then you can just do 2D prefix sums here, and then boom, you can count the area. And then if like a dpij is painted like k times, right, this is part of the area that's painted k times, then answer plus plus, right? Because that's just how you count. Like you can check it. Well, I don't know how why Haybale stacking is considered. Oh yeah, you can also do 1D prefix sums, but imagine. Okay. See the corners. Okay, let's do um the lazy cow. This is not an easy problem whatsoever, actually. So they said it was an easy problem. It's not. I didn't even understand the 45-degree rotation. If you didn't get this problem, it's not an easy problem, okay? This is not an easy problem. I would say it's at least a normal problem. In fact, the grid rotation makes it like a hard problem or very hard problem because to understand the grid rotation, you need to understand like some rotation matrices and stuff like that. Like I can show you like one of the user solutions said it was a very hard problem, like right here. Let's not waste time, but that's what I'm saying. But how do we do a lazy cow? I remember this. Basically, what I'm going to do is I'm going to prove that the shape is always a diamond, and it's pretty easy. You know that if you start at, let's say, a dp of ij represents the sum of all the cells you can reach from ij. So this represents the sum of all the elements that you can reach. Well, then you know that you can add an element a I minus x or I plus x, and you can also add an element or j plus x. So you can move. This is like your total movement. So j plus y, if and only if, or actually, if and only if. Wait, I think it was like this. Or if and only if. Yeah, this if only this is k. What up? There's a better way I did this though. There's or this actually, or this. Let's say you want to add like an element. Let's see you want to add an element a x and a y. You can reach so let's say this is the 2D array is the 2D array is a. You can add this to the sum of dp of ij such that dp of ij represents the sum of all the elements that you can reach. You can add this element if and only if the distance like this plus minus j is k, is less than k. And this forms a diamond on Desmos, and it's very easy to graph yourself. But if you're still not convinced, you're still doubted, you could literally just plug this into Desmos. And let's say ij is 0 for simplicity. Then, how do I do this? Wait, how do I do this? Um, oh, so let's say K is one. Let's say K is one. See, it's just this is basically the diamond. So I proved that it was a diamond. So I think that suffices as doing the problem because I just proved why it's a diamond with math. And um also, and then they did a grid rotation in the solution. It was like they didn't even explain why. Like it was just such a terrible solution. I'm sorry, the editorial is garbage. I don't care. Like even if the person like you're so smart, but I doubt the person who made the solutions is watching this video. But the editorial is garbage. I'm sorry. I did not understand anything. Maybe I'm dumb. I'm probably am, but I don't know. But the instead of doing the grid rotation, you can actually just do 2 pointers. That's what I did, and that's what another solution did. If you go to well, we're not allowed to view the solutions, even though I kind of showed you, but you could just do 2 pointers, right? Like start from 0 to I, and then like or no, just do 2 pointers, right? Keep a pointer to the left and right, and then you know that L minus one, L plus one, and then R minus one, and then L plus two, R minus two, and then you can do it such that you can keep doing it such that L and R are equal, and you could just keep doing 2 pointers on that, and then but you know that you can just do an array of 1D prefix sums, and that's your answer. You don't actually need 2D prefix sums. You can just do an array of 1D prefix sums and then do 2 pointers to fix the left and right endpoints or the endpoint, the points, the end point and start points, and boom. And that's what you can do for lazy cow. Um, I'm not explaining. Like, remember, I have to explain this fast, so I'm not. If you want me to do like an in-depth video for any of these problems, please enlighten me. I haven't this problem in a while, so oh no, I have not done this problem in a while. Like I have actually not thought of this problem in a while, so oh wait, crap, no. Flammerdron's largest pasture can be. Oh my god, this problem's actually kind of toxic though. All right, so from what I can remember, if you have like I actually have not done this problem in a while, but if you have a bunch of points, right? So you have a bunch of points. I think what you do is you do like um oh, and yeah, they're not gonna be on the same. Yeah, so they're all gonna be a unique x and y. They will never be a repeat of x and y. So what you do is you do a vertical line sweep, right? You fix and you go through every pair. So if you fix this one, right, then you go through everything. So that would be like n squared. And then what you can do is for that fixed line, you need to count like the amount. So let's say it's this, right? So you need to count let's say you have this, or I don't want to, right? But yeah, and then you fix yeah you fix like a line, and then you sweep through this, right? And then for each line that you sweep, like in that, let's say you get to here, um or yeah, access here, you need to count your answer in this window. Yeah, you count it in this window, such that this is your you yeah, I think what you do is that this basically fixes the top and left corner if you do it like this. So you're fixing the top and left corner, or not the top and left corner. You're fixing the down left corner and the upper right corner. So or the bottom left corner and the upper right corner. You're fixing those by you can do a vertical. It doesn't really matter which way you can do it. You could also have done it like this, where you do it like this, but you fix that, and then or yeah, or not, you don't do that, but you fix it like this. Like you, this is how you sweep it. This is not, you're not fixing the bottom, and you're not fixing these to be, but you're fixing these 2 points to be on your rectangle, and then you can count like how many like other rectangles you could form. So this is one rectangle, right? But then you can count the amount of rectangles you could form here by the amount of points that are above here, the amount of points that are below here. So it'd be like above times below, um, or whatever, and this plus one, and that would be your answer. And we did solve this problem, but I did not get this obviously when I did this because like I kind of just choked. You don't really need 2D prefix sums. You could just, yeah. I think that this is also a good problem to do again. Um, but yeah, that's basically, you could do you could also do an array of 1D prefix sums. It doesn't really matter. Yeah, I should. Yeah, I probably should have mentioned that to count the amount of points above here and the amount of points below here. Then you just do prefix sums. That I should have. Yeah, that's actually not that obvious though. I mean, yeah. So we still solved it. Boohoo. Because yeah, apply prefix sums there, but I didn't mention that explicitly. So yeah, that one's like, yeah. I'm gonna think. I'm gonna look at that though, because honestly, it's like you're fixing it and you're seeing how much you can get in a window, and then it's very smart. It's just a very smart solution. So yeah. Painting the barn. This is basically painting the silver. So we're gonna copy paste painting the silver. We already know how to pre-compute the canes paints, and then this is basically just like, I already read the problem. As you can tell, this is a recent problem I've done. So what you do here is you have the array, the 200 by 200 or whatever, right? And what you do is you already know how to do the painting the silver, so you can just copy and paste it. You basically do horizontal, because you define disjoint rectangles as there exists a line between those rectangles. And so if you split like the grid at C, then in order to optimize this case where you split the grid at C, you need to find the maximum rectangle sum here. Oh wait, I should. Oh shoot, I also need to specify, because I recently did this problem, so it's not really that fresh. I also need to specify if a rectangle is covered by k paints and k minus one. We only care about these rectangles that are covered in k paints and covered in k minus one. And for each one of those rectangles, or for each one of those like cells or grids on the thing that's covered by k or k minus one, we put a one or negative one, and if it's not any of these, we put a zero. And then what we can do is we can like find, we can do like, the rectangle will just be a gain array like that, like the so we're trying to find uh like the maximum gain here plus the maximum gain here, right? And then that's basically what you would make, like a 2D gain array that basically does 2D prefix sums of a matrix that's a combination of one, negative one, and zero, based on the fact that if you were to paint k, or this should actually be inverted, if you were to paint k, you would lose negative one. If you were paint k minus one, you would gain one. And then if it wasn't k or k minus one, you would gain nothing. You do 2D prefix sums on that to get the rectangle. And then for the case that you split the grid at C horizontally, then the optimal answer for that case would just be the maximum gain here plus the maximum gain here of some rectangle. And then yeah, you can do this for every such horizontal grid, and for every vertical one. And then also what should be said is, how do you actually find the maximum? Well, you just apply Condain's algorithm in 2D. So what you do is, like here, you can like fix like you can one thing I've noticed with like rectangular pasture and painting the barn is like a bunch of fixing. You can fix like one of the like a fixing like a line or something. You can fix like the for a rectangle is defined as the row arguments and the column arguments. So you can fix the row arguments or the column arguments. It's symmetric, doesn't matter. And then you note that basically if you have this already fixed, then let me actually fix them in this color. If you fix these row arguments, then you know that you can start finding the sum of this rectangle. And if the rectangle goes below zero, then you start a new sum, and then you keep doing that, and you can find the maximum. And so then, what is the time complexity of this? Well, then you know that you need to split the grid in. You know that when you split the grid, let's say this is x and this is y. Then to split, you need to split the you would fix x choose 2, and then you need to do this for each column. You could do prefix sums to find the maximum sum. I'm not gonna explain that in my solution because that should already be obvious on how to do that. So we're talking about a Go problem. So it'd be 200 times x choose 2 plus 200 times y choose 2, and that would be 200 times x choose 2 y choose 2. You do this for everything. You also do vertical. um, what am I also forgetting? This is what you do for this, and then you would do this for uh, you do you. So this is 200 times x choose 2. For me, split this. There's 200. Oh, and there's 200 of these splits. So you already have 200 cubed times x choose 2 plus y choose 2. And you know that 200 to the fourth over 4 is going to be the safe estimate because it's 10 to the 8. This is equal to 10 to the 8, by the way. It should be, right? Yeah, it's equal to, this is basically the amount of operations you can do, 400 million. Um, in USACO. Wait, shoot, is that even? Wait, 3. Yeah. So then you know that this quantity is going to be like a very good constant factor. Like it's not going to be 200. This is not going to be 200. Remember, this is like x choose 2 plus y choose 2 is not the same as x plus y choose 2. It's actually going to be less. Like if you just play around with it, like if you do like 6 choose 2 plus 6 choose 2 versus 12 choose 2, like 6 choose 2, that would be 30, right? And then I don't know what 12 choose, well, 12 choose 2 is like going to be 66, right? I do know, I thought that was going to be hard to compute notes on. 12 times 11 over 2, right? That's be like 66, and this would be 30. So you can see, and you can just play around it with more as it increases, and stuff. Like, so you know that like it's going to be different. So this will be, you're getting close to the time, but it's going to pass. So don't worry about that. So I've already kind of proven that it would pass. Now the last problem, modern art, which wasn't too bad. Actually, this is actually, in my opinion, easier than the painting the barn gold. I think they just put it very hard because it's Plat. You know, you kind of need to put very hard if you're putting in a civil module. But no, this problem is actually easier than painting the barn, in my opinion. But don't be too intimidated by the name Platinum. I think anybody in Silver would be capable of solving this if you had a good grasp of the prefix sums module for TD prefix sums. But basically, for this, what you can do is you keep track of the so for an element on here, for an element on the, so let's say called the 2D array A of ij, right? Um, you can read the problem, by the way, obviously. For you keep track of the top index, the top, or the or call this top or call this up, whatever. This will give you the least row index, and then you can also have up, or no, you can also have down. This will give you the highest down row index of this element, and then you can also have left and right. Left will give you the least column index, and right will give you the highest column index. And then what you can do is that basically what you know is that's just basically like for this rectangle to, you can get like, because you know that the rectangle formed by this is going to be obviously uh this to this, right? um or not that, yeah, well, you know that that's basically what's going to form. This is basically just to figure out like the boundaries of your rectangles. And then you know that the boundaries of your rectangles, like if there is like in the boundary of the rectangles, like if there's another number in the boundaries of your rectangles, you know that that had to be painted first, because there's no way that you can like, there's just no way like like no, not that it had to be painted first, that you know that if it it had to be painted later, because there's no way that it could be painted at first, like it just covered something else, obviously it was painted later, right? So that's obviously true. And so, but it's obviously, if you do that type of technique where you iterate through all the boundaries, that's just gonna be too slow. So what you do is you do 2D prefix sums. You say, you calculate the area of the amount of times this is painted, right? And if 7 is painted, you know that if you do that, then this cell will be painted more than once, because this 7, right, belongs to two rectangles. It belongs to this rectangle, like this rectangle, or I can't really. It belongs to this rectangle, right? And also, and then it also belongs in this rectangle over here. So you know that if you do 2D prefix sums, like from how many times it's painted, you know that like that can, you know that it's gonna be painted more than once. And then any time that it's painted more than once, you can basically like say that that color is no good. And then you know that if it's no good, then it won't be a part of your answer. Like the idea of this problem is that um, you know that when you compute the 2D prefix sums for the amount of times like a cell has been painted, if a cell has been painted more than once, then anything, then like you're basically computing the amount of times um an element on the 2D matrix has been painted. And if that element has been painted more than once, well, then obviously then that number is not going to be valid, because that's the last number that was painted, and it was painted more than once. And you can easily like pre-compute that if you have the top and left corner. It's a very clever solution, in my opinion. I just don't know how you would kind of think of that, though. It's just very clever. I'm trying to find motivation. For this. I know the time is. I don't really care about the time. I do. We'll stop it at 75 minutes, anyways. But I'm trying to find motivation for this. I really don't know. Hmm. I guess the motivation will be to see that like 7 belongs into more than one rectangle. So like if you can say that like a cell is painted, if you can say that this isn't, or no, actually no, not painted. Actually, no, that's not that bad, because you know that 7 belongs to this rectangle, because that's what you're trying to that's what you're trying to compute anyway, right? You're trying to say that for a for 7, or like how many rectangles have been drawn over 7. Well, it's just going to be this rectangle and then also this rectangle, so it'll just be 2. So you can pre-compute that with just 2D prefix sums. Yeah, that's not that bad. It's actually not that bad. All right, yeah, and then that's the motivation. Never mind. Then it would be not that bad to think of then. Yeah, so that's the solution. You'd have to use 2D proof sums. I'm not really going to draw that out, but yeah, we just went over. I can stop the timer in 75 minutes. Basically, we essentially talked about all these problems, which I think it's a good idea to do this. Like once you finish problems, make sure you just like go over them, like, and not waste them, and make sure you understand the problems. Like I think this is a good idea to do this a lot for other stuff, because it makes you like have a good understanding of those problems, so that you're not just wasting your time doing problems. You want to get the problem solving aspects, and you want to like be able to do the, like if you can't do a problem, like if you do a problem and then you come over it, and then for like a week later, or a day later, or something like that, even a day later, or like a month later, But if you can do a problem a month later, then you're just, and if you have to redo it, then you're just wasting your time. You haven't learned that problem. You haven't learned the problem solving techniques behind it. But yeah, this is just prefix sums. Hopefully, we can do this for coordinate compression. Uh, this will probably be shorter, but because there's only this many pages. But yeah, that's it. I'm gonna stop